All right, so today we're diving deep into something pretty fascinating. It's called GR00T N1.
Yes, GR00T N1,
And it's all about
a foundational model for generalist humanoid robots.
yeah, so like we're not talking about just robots that can do one specific thing really well.
Right.
We're talking about robots that could potentially, do a lot of different things.
Yeah, like a more general intelligence that could be applied to various tasks and various embodiments.
And they used a lot of different sources for this, right?
Yeah, they really tried to overcome this problem of what they call data islands.
Data islands.
Yeah, so like you have all these different robots in all these different labs collecting data kind of in isolation.
Right, each one is its own little island.
Yeah, exactly. And so it's hard to get like this really massive, diverse data set
Okay.
that you need to train something that's more general purpose.
So they try to fix that by
Using real robot trajectories, human videos, and then also a ton of synthetic data.
Okay, so I'm already curious about the human videos. Like,
Yeah.
how does that even work? Are they just watching us and trying to figure out how to move like us?
Well, that's one of the academic innovations that we're going to kind of unpack today.
Okay.
But yeah, the idea is that human actions, even though we have different bodies than robots,
Right.
like the underlying principles of how we grasp and move and manipulate objects, there's a lot that can be transferred.
Yeah, just from observation.
Yeah, and then they use the synthetic data to kind of bridge the gap
Okay.
and create like robot-specific examples from those kind of more general principles.
So today we're really going to try to understand what makes GR0T N1 tick.
Yeah, like what are the core academic contributions here?
What are the new ideas that they're bringing to the table?
Exactly.
All right, so let's get into it. What's the core intelligence here? What's the underlying framework that allows it to interpret and act?
So at the heart of it, it's a vision language action model.
VLA.
Yeah, a VLA.
Okay.
And so that means it takes in visual information, it understands language instructions,
Right.
and then generates actions.
Okay.
But what's really interesting is that they use this dual system architecture.
The old system.
Yeah, and it's actually inspired by models of human cognition,
Okay.
like Kahneman's thinking, fast and slow.
Oh, wow, for robots.
Yeah, they're applying those concepts to robotics.
Okay, so how does that even work? How do you have like a fast and slow system in a robot?
So they have these two systems that kind of work together. Okay. And system two is what they call a visible language model.
Okay.
Or
Like,
VLM, right?
Yeah.
And that's built on top of NVIDIA's Eagle 2.
Okay.
So that's kind of the more deliberative analytical part of the system.
It's like the thinking part.
Yeah, it's processing what it sees, understanding what you're asking it to do.
Like literally understanding language.
Yeah, pass me the screwdriver or whatever.
Okay.
And it's trying to understand the environment, the goal, all of that.
So that's all happening in this VLM.
Yeah.
And it's running at 10 hertz on an NVIDIA L40 GPU.
Right. So it's actually pretty fast considering all that it's doing.
Okay, so how big is this VLM?
So the specific model they released, GR00T N1-2B, it's got 2.2 billion parameters,
Okay.
and 1.34 billion of those are in the VLM.
Okay, so the majority.
Yeah, and they report really fast processing times,
Like how fast?
like for 16 actions.
16 actions.
Yeah, it can generate the kind of plan for that in under 64 milliseconds
Wow, that is fast.
on that L40 GPU.
Okay, so that's system 2.
Yeah, that's the thinking part.
What about system 1? What's that doing?
So that's more the action side of things.
Okay.
And that's running a diffusion transformer.
Diffusion transformer. Okay.
Yeah, and that operates at 120 hertz, so much faster.
Much faster. Wow.
Yeah, and its job is to generate the actual motor commands.
To make the robot move.
Yeah, like the precise fluid motions that are needed to execute a task in real time.
Okay.
But what's academically significant here is that it doesn't operate in isolation.
Oh.
So it uses this mechanism called cross-attention
Okay.
to directly take into account the output of the VLM.
So they're talking to each other.
Yeah, so the high-level understanding from System 2 is directly informing the low-level motor control from System 1,
Okay.
and they're tightly integrated.
So it's not just like they do their own thing and hope for the best.
No, it's much more of a coordinated effort. Okay? And to make this work across different robots.
Right, because every robot's going to have a different body.
Yeah, different mechanics.
Yeah.
So they have embodiment-specific encoders and decoders
Okay.
that are part of the diffusion transformer.
So it can translate.
Yeah, so it can translate the general plan from the VLM into the specific joint movements and forces that a particular robot needs.
So they don't have to engineer a whole new system for each robot.
Right, exactly.
That's pretty clever.
It's a really neat approach to achieve adaptability.
Yeah, so it's not a brain for each body. It's like a brain that can learn how to control different bodies.
Yeah, exactly.
How do these two systems learn to work together so well?
So another key academic contribution is that they do end-to-end joint training.
end to end.
Yeah, so both the VLM and the diffusion transformer are trained simultaneously.
So they're learning together.
Yeah, and that allows for a much more nuanced and efficient learning process.
Okay.
Because they're learning as a whole.
They're not just like separate components.
Right.
And then you kind of hope they talk to each other.
It's all happening together.
Okay, that makes sense. All right, so we talked about this dual system architecture. Now let's dive into the data.
Okay.
You describe it as a data pyramid?
Yeah.
What's the academic thinking behind that pyramid?
So it represents their strategy for using different types of data that have different levels of generality and embodiment specificity.
Okay, so like a hierarchy of data.
Yeah, at the bottom we have the most general data. It's like web data, human videos, tons and tons of data.
Yeah.
And this has low embodiment specificity because it's not tied to any particular robot.
Right, it's just like general knowledge about the world.
Yeah, but it provides this really broad understanding of the visual world and human behavior. Okay, so it gives the model these broad priors.
Prior's like kind of a baseline understanding.
Yeah, like a foundation.
Okay, what about the next layer?
The next layer is synthetic data.
Synthetic.
And that's generated through simulation and, importantly, also through these pre-trained neural models that can imagine and create new scenarios.
Oh, wow.
So it's like AI generating more data for AI.
Exactly.
And that has medium quantity and medium embodiment specificity.
So it's more specific than the general human videos, but...
Yeah, you can create these simulated environments and robot actions that are more targeted.
Okay.
But still, you have a lot of control and you can generate a lot of variety.
Okay.
So it kind of bridges the gap.
And at the very top of this pyramid...
The top is the most specialized data. It's real-world data.
Real robots doing real things.
Yeah, so that's the most embodiment specific.
Okay.
And also the most challenging to acquire in large amounts.
Of course.
Because you have to have the robots, you have to collect the data.
It's expensive and time-consuming.
Right, exactly.
But it's also the most valuable because it's the real deal.
It's grounded in reality.
Yeah.
Okay? So the idea of the pyramid is you have this broad base of knowledge.
Right.
And as you go up, you're getting more and more focused and grounded in the realities of robotics.
Okay, so the model starts with the general stuff and then fine-tunes with the more specific stuff.
Yeah, and they use a co-training approach that allows the model to learn across all of these layers.
Okay, so it's not just like separate training phases.
No, it's all integrated.
That makes a lot of sense. Okay, so we have this dual system architecture.
Yes.
We have this data pyramid.
Yes.
Now let's get into the really juicy stuff.
Okay.
The core academic innovations.
Nitty-gritty.
Yeah, what are the big theoretical and methodological advances that GR00T N1 is making?
So there are several really novel contributions here. Okay, let's hear them. The first one is that dual system computational architecture itself.
Okay.
Like the fact that they're integrating this VLM for high-level reasoning with this diffusion transformer for generating continuous actions in real time.
Right.
That within one unified learning framework.
Yeah.
That is very different from how traditional robotic systems have been built.
Yeah, it's more like separate modules.
Right, they're more modular.
And this is like everything talking to each other all the time.
Exactly, and that's really key to its capabilities.
Okay, so that synergy between the reasoning and the action generation.
Yeah, that's a primary innovation.
Okay, what else? What's the second big thing?
So the second one is their pre-training strategy.
Pre-train?
Across this really diverse data landscape.
Right, all those different layers of the pyramid.
Yeah, so they have these techniques for incorporating the actionless data.
Yeah, we talked about the human videos.
Yeah.
So they can learn from that even though there's no explicit action labels.
Exactly. So they have this latent action code book.
Latent action code book.
Yeah. It's like a compressed vocabulary of movement patterns that the model learns just from observing.
Just from the visual changes.
Exactly. And they also use this inverse dynamics model, or IDM.
Okay, an IDM.
Yeah, and that learns to predict the forces and torques that would have been needed to produce those motions.
Oh, wow. So they can kind of reverse engineer the actions.
Exactly. And by doing that, they can treat these actionless videos as if they were demonstrations from different embodiments.
Okay.
Even human ones.
So they're expanding their training data significantly.
Yeah, and they have a figure in their paper, figure 4,
Okay.
that shows how similar latent action codes can be extracted from very different agents.
Like humans and robots.
Yeah, humans, different types of robots.
Wow, so they're finding common ground in the way we move?
Yeah, it's really cool.
Even though we have such different bodies?
Exactly.
Okay, that's amazing. What's the third big academic contribution?
The third one is that they've trained this massively multitask language condition policy.
Okay.
So one model that can control a wide range of robot embodiments.
From simple to complex.
Yeah, like from tabletop manipulators to humanoids.
Okay.
And it can also adapt to new tasks really quickly.
Wow, so it's not just limited to the things it's been trained on.
No, it's very flexible.
Okay, so that speaks to a high level of abstraction.
Yeah, it's learned these general principles that it can apply to different situations.
Amazing. What's number 4?
So the fourth contribution is their use of action flow matching and a diffusion transformer for action generation.
Okay.
And they process actions in chunks.
Chunks.
Yeah, so they call it a horizon of H16 time steps.
H16, okay.
And then they use a K-step denoising process.
K-step denoising.
Yeah.
Okay.
Specifically K4 in their implementation.
Okay.
And that refines the motor commands.
So they're really fine-tuning the movements.
Yeah, and they have a specific loss function
Okay.
that's presented as equation 1 in the paper.
Equation 1, all right.
And they use a beta distribution for sampling the time step in this diffusion process.
Okay, so that's getting pretty technical.
Yeah, but these are all specific technical contributions to the field of robot action generation.
Okay, so they're not just using diffusion models off the shelf.
No, they're really tailoring them for this specific task.
Okay, that's impressive. What's number 5?
Number 5 is their approach to synthetic data generation.
Okay, we talked about synthetic data before, but
Right.
what's new here?
So they fine-tuned these large-scale image-to-video generation models.
Image to video, okay.
Yeah, specifically 192.1-I2V14B.
1.2.1-I2V14B, right?
And they fine-tune it using their real robot data.
So they're taking a model that's already good at generating videos.
Right.
And they're making it even better by training it on real robot data.
Exactly. And this allows them to massively scale up their training data.
Okay.
So they generate 827 hours of synthetic trajectories
827 hours.
from only 88 hours of real-world demonstrations.
Wow, that's like almost 10x.
Yeah, it's really impressive.
That's a lot of data.
It is.
Okay, so they're really bridging the gap between simulation and the real world.
Yeah, and they also use multimodal LLMs to prompt these generation models.
LLMs, okay.
Yeah, so they can give it different task descriptions.
Okay.
And then filter the generated videos to make sure they align with the language.
So they're making sure the synthetic data is actually relevant.
Exactly. And they have some really cool examples in Figure 5 of their paper
Okay.
showing these generated videos driven by novel language prompts.
So they're not just simulating physics, they're like imagining new scenarios.
Yeah, it's really sophisticated.
Okay, that's awesome. What about number 6? What's the 6th big innovation?
So the sixth one is dexmimikin,
Dexmimigen. Okay.
which is another way to scale up their simulation trajectories.
Okay.
And they do this by decomposing complex human demonstrations into these object-centric subtasks.
Object-centric subtask. Okay.
So like break it down into smaller pieces.
Okay.
And then dexmimigen can adapt and recombine those subtasks to generate new scenarios.
In different environments.
Yeah, and it's really effective.
Like how much data were they able to generate with this?
They generated 780,000 simulation trajectories,
780,000.
equivalent to 6,500 hours of robot experience.
That's a lot.
Yeah, and they did all of that from just 11 hours of initial human demonstration.
11 hours turning into thousands of hours.
Yeah, it's a huge boost.
That's amazing. So they're really tackling this data bottleneck. Okay, what about number 7?
So number 7 is maybe a little less flashy,
Okay.
but still really important.
Okay.
It's about standardizing action spaces
Action spaces.
across all these different robots.
Right, because every robot moves in a different way.
Exactly. And that's a big challenge when you're trying to build a generalist model.
Yeah, because the model needs to understand how to control all these different bodies.
Exactly. And they go into detail about their specific techniques in Appendix D.2 of their paper.
Appendix D.2. Okay.
But some of the things they do are like using a 6D rotation representation,
Okay.
axis angle representations for joint movements,
Okay.
min-max normalization to bring all the dimensions to a common scale.
Okay, so it's all about creating a unified language for movement
Yeah, a common interface.
that the model can understand.
Exactly.
Okay, that makes a lot of sense. What about number 8? Is there an 8th big innovation?
Yeah, there's one more. Okay. And this is about incorporating an auxiliary object detection loss during training.
Auxiliary object detection loss.
Yeah, it's a mouthful.
Okay.
But basically, they're trying to improve the model's spatial understanding.
Spatial understanding.
Yeah, like its ability to know where objects are in the environment.
Okay.
So they have this extra task where the model has to predict the bounding boxes of objects.
Bounding boxes. Okay.
Yeah.
That makes sense.
And they use this model called OWL-V2 to get initial bounding box annotations.
Okay.
And then they optimize this prediction using a squared loss function.
Squared loss. Okay.
And that's described in Appendix E of their paper.
Appendix E. All right.
But basically, it's helping the model ground the language understanding in the visual context.
So it's not just about understanding the words.
No, it's about understanding what those words refer to in the environment.
Yeah, like if you say pick up the cup, The model needs to know where the cup is.
Exactly.
Okay, so that's a really comprehensive set of academic advancements.
It is.
But how did all of this translate into actual improvements in the robot's capabilities?
So they did a lot of evaluations.
Okay.
And GR00T N1 consistently outperformed their baseline models.
Baseline models. Okay.
Yeah, they compared it to BC Transformer and diffusion policy.
Okay, those were the other models they were testing against.
Right.
Okay.
And it outperformed them across a bunch of different simulation benchmarks.
Simulation benchmarks?
Yeah, things like Robocasa, Dexmimichin, and their own GR1 tabletop environment.
Okay, so in simulation, it was already showing promise.
Yeah, and it even performed well when they reduced the amount of training data.
Okay, so it's data efficient.
Yes, very much so.
But the real question is, how did it perform in the real world?
Right. Simulation is great, but
It's got to work in reality.
it has to work in reality.
Yeah.
And they tested it on their GR1 humanoid robot
Okay.
across a bunch of different manipulation tasks.
Like what kind of tasks?
Things like pick and place,
Okay.
articulated object manipulation,
Okay.
industrial assembly tasks, coordinated two-arm tasks.
So like real world stuff.
Yeah, stuff that would be useful in the real world.
Okay.
And again, GR00T N1 significantly outperformed the baselines.
Okay, so it wasn't just a simulation fluke.
No, it really translated to real-world performance.
And how was the data efficiency in the real world?
That was really impressive, too. Okay, so they found that GR0T N1, when trained on only 10% of the real-world data,
10%.
it often performed as well as or even better than the baselines that were trained on the full data set.
Wow, so it was learning a lot from that limited data.
Yeah, and that really highlights the power of the pre-training and the synthetic data strategies.
Yeah, it had a good foundation to build on.
Exactly.
Okay, so it was better quantitatively, but what about qualitatively?
Yeah, they also looked at the quality of the robot's actions.
Okay.
And they found that GO0T N1 had smoother, more natural motion,
Okay.
higher grasping success rates.
So it wasn't just doing our task, it was doing it well.
Yeah, it was doing it smoothly and efficiently.
Okay, so that's really promising.
Yeah.
And they've released all of this publicly, right?
Yes, so they released the GO0T N1-2B model checkpoint,
Okay.
the training data, the simulation benchmarks.
So other researchers can build on their work.
Exactly, and that's really valuable for the research community.
Yeah, it's a great contribution.
It is.
Okay, so to wrap up this deep dive,
Yeah.
what are the key takeaways about GR00T N1 from an academic perspective?
So the main innovations are that dual system architecture
Okay.
that integrates reasoning and action generation,
Yeah,
their data strategy.
the data pyramid,
Yeah,
using real, synthetic, and even actionless data.
exactly.
And their massively multitask language-conditioned policy.
One policy for many robots.
And their advanced techniques for action generation.
Using diffusion models.
Right.
And their groundbreaking methods for generating synthetic data.
Bridging the gap between simulation and reality.
Yeah, and all of this leads to a really effective and data-efficient system.
That's really impressive.
It is.
It sounds like a big step forward for general-purpose robotics.
Yeah, it's a very promising direction.
But are there still open questions?
Oh,
Like,
absolutely.
what kind of things are researchers still working on?
So one big question is how to scale these models to handle longer horizon tasks.
Longer horizon? Okay, the tasks that take more time.
Yeah, tasks that require more steps, more planning.
Okay,
And then another big challenge is improving the synthetic data generation,
right.
making it even more realistic.
So it can better prepare the robot for the real world?
Exactly.
Okay, so there's still work to be done.
Yeah, but this is a really exciting field.
It is.
And GO0T N1 is a major contribution.
Yeah, for sure.
If you want to learn more about the technical details,
Yeah,
we have links to the paper and the open source resources in the episode notes.
definitely check those out.
And, maybe you can even contribute to this research yourself.
Yeah, if you're feeling ambitious.
Yeah, why not?
Okay, well, thanks for joining us on the deep dive.
Yeah, thanks for having me.
It's been a really fascinating conversation.
It has.
Oh, we'll see you next time.
See you later.